Hello, my name is Jenny Shatts. I am presenting the integration and test strategy for the Orbiter UPSM Pro vehicles. My team includes my colleagues Alex Ventura and David Foster. Next slide.
None of those are looking for a job?
Oh, definitely. I graduated in June. Sorry. The integration and test team had to work within several restrictions and assumptions. First being that our facility only has one of each of the following test apparatus: one thermal vacuum chamber, one acoustic chamber, one shake table, and one anechoic chamber for RF testing. Since the probe is descending into an atmosphere and needs special tests for that, and we are typically a spacecraft assembly facility, we cannot provide such things as a wind tunnel or an arc jet. The largest constraint we've had to deal with is handling of radioactive material. As you are well aware, we are using ASRGs and RHUs. These items really shaped our assembly order as well as how we scheduled when these would be integrated. Next slide.
Great, thank you. These restrictions, this is for all the testing through the entire program. You've only got one, should be?
Yes.
So there's one chamber that's going to test the unit that's like this size and the entire integrated spacecraft?
To address that question, we are assuming that the subsystems will take care of the unit level test. So when
so this is just for the spacecraft?
This is spacecraft.
Okay, fine. Okay. That's better. I can deal with that.
Okay.
Otherwise, you just guys aren't prepared for this program. So
we're thinking ahead.
Your test program too.
All right. We also are making sure that we meet all the MIL standards, especially number 1540, that helps guide us with testing procedures for units, components, and system level. Next slide, please. The INT team tries its best to maximize accessibility while assembly, as well as maintaining a flexible schedule. This means that components and hardware are easy to reach for employees making the spacecraft, as well as making sure that these components can possibly be integrated at different times in the schedule if needed be. In general, our philosophy is test like you fly, fly like you test. We do deviate from this a few times, and what I'm about to say is a little bit contradictory from what I answered a question earlier. In environment testing, our thermal vacuum chamber cannot or may not go as low as the expected temperature at Uranus. The expected temperature around there is around 50 Kelvin, and that could possibly mean that we would need liquid helium to cool the thermal vacuum chamber. Our customer has not identified whether we do have that capability or not. But to get around this, we can implement more rigorous analysis to validate that our spacecraft could survive this environment. Next, we are not going to be doing a vacuum deployment test at the system level. This is a really complicated test. This is because it costs a lot of money. And we know that we can qualify this at the unit level and make sure we have allowed more time to qualify this part.
Do you mean you're going to have it integrated with a mass simulator or with a magnetometer on the end of it, and you're going to deploy that as an assembly, not deploy it on the space beach?
Precisely.
That's what you're doing?
Yes. All right. Moving forward, there is also, we are going to be doing a probe shock test only before thermal vacuum. This is because we want to make sure we can do all of our shock testing all at once. This includes our launch vehicle shocks, and then at that time, right afterwards, we're going to be doing our probe shocks. If we, rather than doing it shocks before thermal vac, and then once again after.
I got a question
yes.
To that. So I think previously you said that you expect the subsystems to do their testing before they deliver to the spacecraft level. I would expect the same thing on the probe, right? I would expect the probes to go through their environmental testing before they deliver to you, and then test the systems. So why are you doing probe shot testing there before they deliver back?
This is with respect to each carrier vehicle, that we would like to do there is a separate shock test that the probe does by itself, which will be addressed later, but we're talking about the shock test from when you have the carrier vehicle, such as the orbiter and the probe, and then the probe is dropped. We want that particular shock scenario is what I'm talking about.
Impacting the vehicle, the orbiter.
Yes.
I'm sure we do that with a mass model. You don't need a probe for that. You probably should do that with a mass model. And not break your probe.
When do you do the thermal back on the probe?
When? For the probe, that will be addressed in a later slide.
Okay.
And it will
I'll
be
wait.
Thank you.
You mentioned environmental, electromagnetic environmental effects. Are you concerned about that? How do you address that?
For
EMI is electromagnetic environmental. Radiating emissions, production emissions.
how are we testing for this
Well,
scenario?
yeah, normally you would do testing in box level subsystem
Yes.
system level, perhaps, depending on how you determine you're going to do it. So what are you doing?
For our EMI testing, I'd like to divert that question to my team.
We haven't really accounted for any EMI testing.
So we'll look forward into doing that later on.
Okay.
Like I said before, we are assuming all the flight hardware will be protocol before arriving to system level testing, and then our system will be then tested at protocol. Next slide, please.
Oh, well, another question. You said testing without flight ASRG, so you have mass model or thermal model or something?
Yes, oh, I forgot about that bullet. Yes, during testing, we cannot use the actual flight RHUs and ASRGs. This is because they will not be available until the launch site. So it will require some sort of substitute, such as a patch heater or some sort of mass model that can radiate the same amount of heat and or electricity during testing. Next slide. Here you can see the mission program schedule. Today we are looking at our conceptual design review. Approximately 2 years later is our preliminary design review, or PDR. That's happening at September 19, 2014. And then later on after that, about a year and a half, is our critical design review, which is March 23rd, 2016. And you can also see how long the 3 vehicles are taking with respect to their program schedules. This is including subsystem manufacturing, then system assembly, environmental testing, pack and ship, and launch operations. Moving forward.
So when you go through the integrated test, you only do one vehicle at a time, right?
Yes, there are certain periods though in our testing where we will have, let's say, the orbiter and probe made it during test time. And then there's going to be some times during environmental tests that they will be separated, and this will be addressed in a further slide, and you'll see that in during the blue schedules represent the actual times where we are doing assembly and, at least for the pro schedule, this includes also includes developmental testing. The gray periods include times where we're doing more analysis or as we move into PDR.
Why is the probe schedule so long compared to the others?
It is so much longer because we are including the development testing required to validate the probe for that schedule. Does that answer your question?
No. What is it you need to validate? That's kind of interesting.
I will talk about that in that next slide.
Okay.
Great.
Are you going to talk about marking and schedule? Maybe identify points of marking?
Yes, we will be able to see that in the upcoming slides where we put a contingency. So, next slide. Here on my left is the probe development testing schedule, and it also will outline the 3 major probe development tests. Here on my right is the probe CONOPS and how we are validating using analysis and those tests to validate that we can do the task seen here. So the first test that I would like to acknowledge is our supersonic wind tunnel and subsonic wind tunnel test. These will validate the aerodynamics of the probe's descent. as well as the drogue and main chute deployment, inflation, and stability. Since this test shall be implemented at NASA Ames. The next major development test is the RJET ablative test. This is needed to validate the heat of ablation as well as the rate of ablation for the front heat shield. And we want to make sure we can withstand the peak heating in descent. And once again, this test shall be performed at NASA Ames. Last major development test is the balloon drop test. This is probably one of the most important ones. This is going to be validating the entire descent sequence under dynamic conditions. We're going to be validating all those components that help trigger all the events during descent, such as separation mechanism, timers, accelerometers, parachutes, etc. Atmospheric similitude between Uranus and Earth was performed in order to see how we can perform this test here on Earth. We would like to use a balloon to take a probe engineering model up to a minimum altitude of 7 kilometers. This probe will then be released, and then we will keep track of this probe as it descends and watch and make sure that all the descent sequences will be triggered and formed. If there are any questions, I would like to move on to the orbiter assembly.
So you're going to validate that critical item at time?
Yes, at that time.
And do you know that the chute test can be done at Ames as opposed to somewhere else?
Can you please speak louder?
Oh, you know that the parachute test can be performed at Ames? I'm kind of surprised.
Yes. Because it has such because of that wind tunnel is so large, and we would like to be able to either have a full-size 1-to-1 scale parachute, or if need be, we can use a smaller scale size parachute just in case. And we can do analysis to see the similitude between the two and make sure we can validate that the parachute can still perform. Does that answer your question?
Well, I'm just kind of puzzled because I believe that the rovers, those tests have to be done in Cleveland. The chute design is a big problem for MER, right? And
Yes.
That testing was not done at Ames. It's done, I think, or somewhere.
Where?
Cleveland.
Cleveland. Okay, I couldn't hear you.
You're
So
fine.
Ames is okay? Okay, cool. All right.
They did MSL shoot test at Ames.
All right. That's why I chose that. Now that I remember. All right. Now let's move on to the orbiter assemblies. I would like you to note that this is not going to, the video that I'm going to be showing here will not be the only way we can integrate the orbiter. This is just one possible scenario. Also, the orientations shown in this video are not indicative of what's going to happen on the ground. This animation starts after the entire structure has been built and assembled. The structure is then sent to the propulsion team to have the propulsion system integrated. Please start the video. First, the tanks are installed into the thrust cylinder and are shown in orange. Next, some of the structures, such as the shear panels, are added, and we'll start running some piping. After some piping has been laid, valves and pressure tanks are added. The rest of the shear panels and L brackets are added next. The rest of the piping and valves are added as well. And the RCS thruster clusters are mounted to the L brackets. Lastly, the main thruster and the supports are added up to the bottom. Here you can see the ASRG panel being assembled with the ASRG control units and PDCs in purple. This panel is then attached to the spacecraft, and the probe panel is added next. Here, the orbiter is oriented on its side so that with a layover cart and ASRG panel facing up. The flight computers shown in green are now being integrated to the shear panel. The communication subsystem components, such as tweeters, receivers, and waveguide, are added in blue. There are some redundant comms components that are hidden on the other side of the spacecraft. Then the ADC subsystem components are added, such as IMUs and reaction wheels, which are in teal. Here, now here, we can see the mag panel being added. The components such as the magnetometer assembly, radiators, and star trackers are added here. And that panel is then attached to the orbiter, and the orbiter will be oriented upright. So now, next, the battery packs are integrated to the inside of the ASRG panel, and then the mag panel is then attached to the orbiter. This is going a little fast. Here it is attached. Now the antennas are then added, and here the instrument panels. The orbiter is then rotated on its side once again to integrate the probe. The orbiter is rotated upward once again to integrate the thermal skirt. And now you have a orbiter ready for environmental testing. Are there any questions?
Well, this may not be a question for you, but just at the system level, have you looked at, I mean, you were showing the spacecraft in different orientations. Are there any problem with, orienting in a certain position with the 1G? Maybe it's okay vertically, but, if you're on a different axis, maybe, it could cause some damage to you.
I'd like to remind you that the orientations and rotations shown in the video are exactly indicative of what can happen on the ground. Does that answer your question?
Is this okay?
Yeah.
Are you worried that if it's rotated on its side, that it could cause potential
I mean,
damage?
sometimes, these things are designed to fly in space. Here you're testing it under a 1G field. Sometimes certain orientations, there's added stresses or forces on components that could damage.
They're also designed to withstand the launch cycle, so.
Yeah, but in a certain axis, right?
Well, that axis, I mean, it's like shake everything.
For structural analysis, we have not yet had a chance to run what it would look like if the structure was oriented 90 degrees on its side and a 1G loading yet.
And you need to install the mass models for the ASRGs and anything else that's not on there before environmental testing.
Yes, that is correct, but that is not included in the video at this time. Moving forward, we're going to talk now about, next slide please, the orbiter test assembly, or testing sequence. This starts, excuse me, my bad. The UPS design is talked about first.
UPS is done well before you order?
Yes, because it has an earlier launch date. So now I'm going to talk about the UPS integration and test assembly. The UPS flow is a little bit simpler than the orbiter flow. This is because the UPS is a much simpler spacecraft. So let's start the video. Integration starts with a mated thrust cylinder and cone. 4 shear panels are added and the bottom panel is attached. Next, the entire L bracket structure is attached. 4 non-removable cross panels are attached to the L bracket structure. The propulsion team comes in and installs its thrusters, tanks, valves, and lines. Shown here. Next, you can now see that the power subsystem components are being added. This includes the PDUs and ASRG control unit. Next, the ADCS components are attached to the spacecraft, most importantly, the IMU shown here. Now, the flight computers are installed under one of the IMUs and on a non-removable panel. Here, you can see an upper panel, including the high-gain antenna supports being installed. The view here shows that now shows a ground-looking up scenario into one of the quadrants of the UPS. Now, the communication hardware is being installed to the underside of this top panel. Here now you can see the high gain antenna being installed as well as the helical probe receive antenna. 3 of the 4 removable panels are attached to the structure as well as 1 star tracker. Finally, the 4th removable panel is attached and a 2nd star tracker is added. And now we have a finished UPS ready for system level tests. Next slide. Now let's move on to the probe assembly. Please start the video. Now, we start with the probe assembly with the equipment shelf facing up. Please integrate the nephelometer and the PDCU first. Then we rotate the equipment shelf facing up to attach the ASI and its components, as well as right now, the flight computers and shown here. And now there's the ASI. Next is the neutral mass spectrometer. And now the constant transmitter is added on top. We now rotate the equipment shelf once again to attach the battery packs to the bottom. Here, you can see the bottom of the descent module being attached. And here is the top of the descent module. Here's a close-up of the helical antenna being attached, and then the main parachute assembly. Next, the top of the descent module is then attached to the equipment shelf, and those two are mated, pressurized, and then a leak test is performed. And now the front heat shield is installed with the separation mechanisms and support brackets. Here is the top heat shield with the drogue parachute assembly attached, and that is then mated to the front heat shield. And the probe assembly is now finished, and we'll now go to the next slide if there's no questions.
Why are the probes different lengths and time to assemble?
This is because we want to implement lessons learned philosophies. So imagine that the first probe takes a certain amount of days, and then hey, maybe we figured out something that we can help improve our assembly. So maybe the subsequent probes take a little bit quicker.
And then maybe you don't. So then are you still at 107 days?
If not, then yes, we would probably be at 107 days. But we do have contingency in the schedule in case that the probe assembly does take longer.
So where is the
That is currently.
We're looking for a different color.
Oh, okay. We added our contingency at the end of environmental test. The specific probe schedule was cut from the presentation, but we will show an orbiter's environmental test schedule that shows its contingency, and I can tell you the contingency for the other vehicles at that time.
We talked about this assembly schedule in the lecture board. So it looks to me like there's enough overlap between the first two that anytime you have problems in the first one, you're going to be scurrying to get it done. So you're not going to learn enough to help the second one. And then you got a year between the second one and the third, which is more than enough time to forget it and you can learn.
I hope that we can record.
You can record till you're blue in the face. And you're going to have a different team do it who's not going to know what to do. I will tell you I've seen it happen. So, I mean, it's what you're suggesting is well intentioned, but the reality is, in practice, it doesn't work the way it sounds. Is what we've seen.
I like your experienced knowledge, and so I will hopefully move forward with that. Next slide, please. Here you can see the orbiter system level test. The order is as follows. We're going to do a functionality test before we move into RF testing. Next, we do our acoustics, then shock, and then thermal vacuum here. After that, we'll do another functionality test, and then do another RF test, and then move into a final end-to-end testing before shipping. Now, the UPS deviates from this schedule very minimally. Because it doesn't have to do a Venus flyby, its schedule is a little bit more shorter.
I'm sorry, what does RF testing mean?
We're testing the transmission of data. So if you're in this is the test.
Talk to the orbiter to the link.
Yes. Also, the probe system level test deviates from this schedule just a little bit because we only have to do shot test for the heat shield separation, and then thermal vacuum, which I know is not shown, but just imagine in your head.
You're doing end-to-end test. Are you doing an end-to-end test in the beginning?
Yeah, I refer to that as a functionality test.
So you're calling something else, but it's not there, but it is there, really?
Yes.
So after your dynamics testing,
Mm-hmm.
do you ever do any tests to validate that your magnetometer reading still works properly and the releases for your probe work properly?
I will defer the magnetometer room question to David Foster.
No, we're not going to test the magnetometer room at this time. We were under the impression that the testing involved, testing a magnetometer room is really complex and would require a lot. So since it's kind of its own component, we figured it could be tested more before it was sent to be integrated on the orbiter, and that should suffice.
But you're going to drag it through spacecraft level dynamics, which it has never seen before. You're depending on the fact that the base inputs to that thing were analyzed properly.
Yes.
So, I mean, you've potentially done something to it different than you tested it to when it was tested at the unit level. So how do you know that you haven't messed up with the point?
Just so you know that during vibes at the system level, the magnetometer is not deployed. It would have been, but
yeah, you're not going to deploy it during 5 minutes. It's launch. You want to validate that one hasn't messed up your ability to deploy it.
So we are assuming that the magnetometer assembly is arriving protocol. We don't want to overstress this boom because it is a vital procedure. So if we did qual testing, that we would potentially creating a program emission risk.
Nobody's asking. I'm not suggesting qual testing. What I'm suggesting is you took it through a set of tests here, and you've taken it through a set of environments that it has never seen before. And you need to prove that it's going to work after that set of environments. Because that environment is the closest you're ever going to see on the ground to what it's going to see during launch. Okay? Because, I mean, to determine what's going to happen at that base point where it connects is non-trivial. You know, and the analysis tools are good or not perfect. So that's really the question.
So your point is to deploy it after you've had vibration and thermal back. And one thing we learned very much the hard way is that we didn't have vibration in thermal back. And that's probably not doable. Well, it is, but not the deployment, of course, doesn't have to be under that condition. But your main point is be sure that it deploys, albeit somewhat assisted, suspended on whatever.
And I mean, you know, in a couple of ways you could do it. Depending on how that thing works, you could just disconnect the whole thing from the spacecraft and take it back to manufacturing and let them deploy it because they've got all the rigs. The other way to do it is to do a release in first motion and then take it off and package it and send it back to them. I've seen both of those things done.
Hopefully
So I'll write.
Yes, we can implement that later.
What's the 11/7/2021 date? I don't understand what
That is the date right before the first date of our launch window. So we want to make sure that we are prepared for the first date of our launch window.
just for the churchmanship, it looks like those of you that
The dotted line show that this system level testing is expanding, so it's not necessarily the time. So if you look at the bottom of the expanded timeline, it's at 5/18/2021.
So is the time of the launch site long because you're integrating all the radioactive equipment there, is that means another almost 3 months?
Yes, and that also includes ASRG and fueling, and which we'll talk about later on. If there are not any more questions, I will move on to the next slide with orbiter launch site operations. This happens after we pack and shipped the orbiter. We first unpack it, which takes some time, and then we do a functionality test to make sure that the orbiter was not damaged during shipping. Next, RHU integration is done next, and because we have so many RHUs, about 90 or so, this does take up a lot of time. Next, the probe is integrated, and finally, the ASRGs are done. And in between probe and ASRG integration is when we do fueling. You'll also note that the, yes, question?
Aren't the ASRGs on the system because of radiation, they're not on the system at all times?
Correct.
Yes, that is correct.
So did you have mass simulators in there for that?
Yes.
That's why great the dynamics. Thank you.
What's your assumption as far as shipping the spacecraft to the launch site? Is it fully assembled or?
Yes, the orbiter will be fully assembled, and then in order to have the RHUs integrated, we do have to take off the probe panel. Which panels need to be removed?
It could be me too, but right now we're assuming the magnetometer and the ASRG, or sorry, magnetometer and instrument panel.
You also note that we are doing ASRG integration before we are encapsulated in the launch vehicle fairing. This is because you'll note that the ASRGs are arranged vertically on the orbiter, so it would be very difficult to go through the door in the fairing to integrate such the ASRG at the very, very top.
You don't want to do that, you wouldn't do that.
Okay.
You wouldn't do that. Once they encapsulate you, you just stay away. That's the way it works.
So which is something that we did kind of.
I'm sorry, where's fuel?
It would be between probe and ASRG integration. It's not labeled, but imagine that gray area being labeled that way.
So you're gonna install electrical power generators and test them and validate that everything's working on a fully fueled vehicle that has 2 chemicals on it that are rather nasty.
We'll be very careful.
After you install these things, you're going to have to go back and
I think you want to think about making the last thing you do before you hand it over to the launch vehicle guys be fueling. Nobody likes to go near these things once they're fueled.
That is understandable.
Well, wait a minute, though, you have to fuel in the explosive safe facility.
Right.
And that's not the patch. So I don't think that works.
Well, it doesn't work. That's how.
Oh, you can't put
You
can't put
load
them on
the
before you
propellants
get to the
in an explosive safe
Yeah,
facility.
I understand that.
And then the last thing you put on the vehicle is the RPG.
Oh.
And you don't want to be spending a lot of time bolting them on either with your nose about that far.
Yeah, I know. I know.
Yeah, they do
There's
that
a story about that.
So you can find people who are even more bizarre than the fueling to do this?
But they'll tell you about it too, okay?
Okay.
So I'm glad that our
Okay, fine. Okay.
Your front page is
They have to be.
And they don't get to wear those big suits either. Like prop backs.
as fun as all these trade, these trade secrets are.
EOD guys. These are like EOD guys. They think it's fun.
Okay. So the UPS deviates from this launch operation sequence in that because it doesn't have RHUs, it can be shipped completely assembled and then have the probe immediately attached to its vehicle. And it will go through the same process of fueling and then What also how it deviates is that we can encapsulate in the fairing before the ASRG is integrated, is what my UPS expert thought, program schedule thought would be best, because we can go through a fairing door. This was cited because MSL's RTG was able to be integrated through a fairing. That was, and also the probe deviates from this launch operation schedule in that it does get shipped to the launch site assembled, but it has to be disassembled for the RIG integration, repressurized, re-leak test, and then all those separation mechanisms need to be reintegrated as well and rearmed. If there aren't any more questions concerning integration and test for any of the vehicles, I would like to hand it off to Steve Katzman for our concluding remarks.